Welcome back, students, from spring break and to a whole new world. All right, I am doing Lab 5 today. I'm recording this as obviously as a YouTube video. And from now on, if you guys got from my message from before, all our lectures will now be recorded as a YouTube video. Now, the YouTube videos I try to get out beforehand, like this is going to take some time. Loading them up takes some time, and then having it standard image and then high image takes a while. So I will try to get it done before our classes. Now, I'm putting up these YouTube videos because I don't know about everybody's internet quality, and I don't know what's going on with everybody's schedule. But this is a great way for you guys to have whenever you guys have internet or bandwidth, you guys can go through these lectures, check them out. Basically, it's the same thing I do in class. I'm going through the slides and I'm typing up the code. Same thing. Now, that's great. The downside is if you guys have an error, you're kind of on your own with the YouTube video. That's why what's happening is our class times, right? Our class times and Tuesday nights, Wednesday afternoons, and Sunday mornings. Those will now, I will use at least not the whole time, but at the start of the time, for example, Tuesday night at 6:40, I'll be on WebEx and I'll send out the WebEx link to everybody. And basically the time our normal class would have started, that's now going to be our weekly office hours, right? So for example, Tuesday night, I'll log on at 6:40. I figure we'll be done by around 7:40, about an hour. And that I'm reserving now for anybody that has any errors with their code or any general questions about the video. That way we can still get that Q&A part that we actually miss out on now that it's a pre-recorded lecture. So if you understand the material and your program works perfectly fine, that's great. You don't have to log in. If you have any kind of issues, then log in at the allotted time. Again, I want to make sure everybody goes at the allotted time because debugging too many people's code at one time, we're not going to have enough time. So that's why the class times now online will be more of a Q&A / fix your code time. Or basically if you want to think about like office hours, like online office hours. And these YouTube videos now are going to serve as your lectures. All right, so let's get started. When we left off, guys, we were doing, we started classification, the machine learning. I introduced you to the concept of Scikit-Learn, and Scikit-Learn is a machine learning package within NumPy. Well, I'm sorry, not within NumPy, within Python that interacts with both Pandas and NumPy and all the other packages. We did this part for most of the classes. We were at different paces. But I'm going to start off from this slide again, only because in case you forgot, right, in the code, right here in my code, I have this stuff from before. I'll write this stuff again, and I'll go line by line again. So if you remember all this, if you have this, if we were way ahead, please forward ahead in the video to where you left off. If you need to review this, by all means, go ahead and review this. Now, as a refresher again, basically what's happening here is there's a very famous data set. It's called MNIST. Within this data set is a whole bunch of images. These images are from the numbers 0 to 9. Okay? These images have their actual answers associated with them, right? And so you have both the training data and you have both what we call the target data. The target data is the actual answer. The training data is the images. All right? So how are we applying machine learning? What are we doing here? Basically, we want to create a classifier. That's a type of machine learning program that will learn how to look at the images and then say empirically what that image number is. The images are from numbers 0 to 9, right? And they're handwritten pretty much. They're handwritten. Basically, they're the images of people, high school students and census takers that have basically written, I have this in the previous slides if you want to go over it, that pretty much have handwritten the numbers 0 to 9. The reason for this is because if you have a classifier that can basically differentiate handwritten numbers from 0 to 9, you can then have a program that takes handwritten numbers and and converts them into digital numbers. And again, that's huge. I don't have to tell you the ramifications and the applications of something like that, right? Anywhere from PDFs to handwritten things, when you're loading them up, we can take them and convert them into digital data feeds, right? That's a huge business in itself. Digitizing historical records and current records as well. Everything's not digital. A lot of contracts, a lot of numbers, a lot of documents, they tend to be hard copy. But even if there's a digital copy, a lot of times people might scan a document and trying to reverse engineer what that document is. You know, machine learning, something like this can come in handy. All right, so from here, we want to, first of all, import NumPy. I have import pandas up there. We don't even use it right now. So we import NumPy. I import Scikit-Learn datasets, import, fetch, open, ML. Now listen, before you even do this part, some of you guys had this problem, make sure and again, I'm starting from a little bit before what a lot of you guys were. If you already remember this, please forward ahead in the video. Now, if you don't have your Anaconda updated, line 10 will fail for you. Line 10 and line 11, all right? Make sure before you do this, your Anaconda is up to date, okay? It'll update all your packages, including Scikit-Learn. Now, the MNIST dataset, again, that I'm talking about, that MNIST dataset is a very famous dataset, like I said before. Anybody that writes a new classifier, a new machine learning algorithm, or program, they always run it against the MNIST dataset, and they see how well they did and if they're better than the off-the-shelf classifiers. Two of them, which we'll look at today, right, in this video. All right, so these data sets are so popular, and there's a whole bunch of them that are very popular in machine learning. All these universities use it, that Scikit-Learn loads them up directly in there. So that's what we're doing here. I'm calling from Scikit-Learn datasets, fetch OpenML, this function, and this function will go ahead and load for me the dataset MNIST_784. All right, MNIST_784. Basically, these images have 784. They're 28 by 28, these images. I execute this, look down here at the bottom right of my window. It's fetching it, it's going to take a little time. On some of your machines, it takes just as long as my machine. A few of you guys are faster. A few of you guys take a while. I think some of you guys took like 10 minutes on your machine to load it up. Like over here, it's probably going to take like 30, 40 seconds here. So for those of you guys that are taking 10 minutes, whatever, you can pause the video at this point. Oh, there, I finished. For the rest of you, if you're waiting, go ahead and pause the video until it loads up for you, then we can continue. Now, if you remember, MNIST is what we call a utils type.bunch. If you double click on this, and again, we're waiting, you get something like this. What the heck is this? Well, utils bunch, or bunch for short, if you guys remember, it's a sort of weird object within the world of Python. It's a dictionary that allows you to store other objects. Normally a dictionary, you have a key value pairing, right? Some sort of key that gives you some sort of value. Here, a bunch, it gives you a key, but that key gives you a whole new data container, right? That's basically the way it works. And if we look over here, oh, where'd it go? Did I lose it? Did I close it? I think I closed it, right? It's all right. I'll open up it again. So here, these are the keys. Here are the datas. Which data we care about? We care about literally data, which gives me a two-dimensional NumPy array, all right? And target, which gives me a one-dimensional NumPy array, and that's the actual values. Notice here it's a float. These are numbers. Notice here it's an object. That's because the target, the target numbers aren't actually numbers. The numbers are given as strings. I don't know why they would do that. We can convert it if we want to, but whatever, we'll leave it as is. All right, so here we go. From MNIST, I go ahead and execute my data part right here. I have my data, and as you can see, data is a float. It's a 2x2 NumPy array. We talked about this already. And I get my target, which as well is an object, strings, and it's a traditional, more one-dimensional NumPy array. From here, I'm going to go ahead and import matplotlib and matplotlib.pyplot as PLT. Now, matplotlib, we just jumped into this. Matplotlib is a graphical tool from MATLAB. All right, it's been loaded into the Python world. It's very popular in MATLAB, so it's very popular here. So we'll use matplotlib. I am a little sad that Python doesn't have it has ggplot, but ggplot hasn't been updated for a while. Unlike in R, where it's constantly updated and they're constantly developing for it. I don't know why they haven't followed up with it in the Python world. My guess is because matplotlib is just so popular, right? So here I'm going to just run these guys, and we'll play with it a little bit later. All right, now what we did here, we took a random digit, a random value. Now again, let's talk about the data table real quick. It's a 2x2 array. You notice there's 70,000 rows, 784 columns. This is a refresher again, 70,000 rows because there's 70,000 images. You see, each image is represented by an array of numbers. An array of numbers. In this case, each image is represented by, each one of the 70,000 images is represented by one row of 784 numbers. Now, why 784 numbers? It is because each one of these images are in actuality 28 by 28 pixels. All right, they're 28 pixels high, 28 pixels wide. And 28 times 28, guys, gives you what? It gives you 784. 704 numbers, or more specifically, in terms of machine learning, 784 features. Each one of our data or our items, right, these pictures have 784 features. What happens is the image was squashed to be a single array. Those 28 by 28 pixels were squashed to be a single array. If I open up an Excel sheet right here, if I could show you real quick, right, scroll in this Excel sheet right here. So let's say hypothetically we had a 4x4 picture, right? 4 pixels down and 4 pixels across. Boom. All right, put some borders in here. Excellent. All right, so we have a 4x4 image. The way NumPy array, the way it was stored in NumPy array, it was stored as a single array. This was the first part. This part right here was brought over here. This part of the image was taken and brought over here, and this part of the image was taken and brought over here. All right, boom, and that's how you had that NumPy, that array. And this is why here we have an array. Each image is represented by an array of 784 numbers or 784 features. Now, why numbers? Those numbers translate into colors, and that's what we did here. This is how we went actually. And again, please, if you remember this, if you have this, please go ahead and fast forward from this point. Here now, I'm going to import pill, the image package from pill. Pill is a very popular, it stands for pillow. It's a very popular image manipulator in the world of Python. I use this a lot in my different web classes and web frameworks, right, to manipulate images behind the scenes in the website. So here, this image allows me to load in and create and actually manipulate images. All right. So I have an image pre-saved on my hard drive. Let me show you what that is. All right, let me show you what that is. So if I go here, open up go to Documents, go to my BAP, Spring 2020. I have an image here called Tesla. Of course I have an image called Tesla. Boom, that's the image. If I want to load this image into my Python, well, first things first, I got to change my folder to that folder where the image lies. So let me go ahead and do that right up here. Remember the black folder, guys? Click on the black folder. And you're not going to select the image. You're not going to select the image. You're simply going to select the folder where the image lies. So for me, it was BAP. spring 2020, and there's the image right there, Tesla. I'm not going to select it. I'm just going to select the folder. Boom. As you can see up here in the URL, again, the image is a change. I'm going to now go ahead and do image.open, the name of that image, Tesla, bloom, bloom, bloom. All right, here, look what you see. You see an image, you see a size, and you see some sort of value here, PNG image. Okay, it's a type image, done. The size, what is that? Is the width and the height. If you remember, I don't know why I closed it. Here is the width, how many pixels wide it is, and how many pixels long it is, high it is, sorry. The pixels of the width and the pixels of the height. Well, the pixels of the width, 944 pixels. The pixels of the height, 464. Easy, not bad. Now, from here, I'm going to use my np, look how cool this is. I'm going to use my np.array command, and I'm going to convert that image into a NumPy array. That's right, convert it into a NumPy array. Boom, I do that, and now you see this NumPy array that is now converted, Tesla NP, into a NumPy array. But wait a minute. Okay, first off, what kind of type is this? We'll talk about that in a second. I'll get back to the type in a second. Let's go to the size. Okay, this is not a single array, right? We have, obviously, it's 464 rows of data. All right, fine. All right, fine. Okay, all right, fine. And each row has 934 columns. Okay, all right. Okay, not bad. What the hell is this third number here? Well, you see, Tesla NP, unlike data was a 2x2 array. Tesla underscore NP is a 3x3 array. It's a cube. It's a three-dimensional array. It has rows, it has columns, and it has depth. Rows, columns, and depth. In this case, it has 4 dimensions of depth. All right, 4 items of depth. All right, and if you remember from last week, the reason it does that is because that image, this image, unlike our images that come from the MNIST data set that are just simply black and white, this is a color image. More specifically, it's a PNG file, which is what we call a RGBA image. RGBA. Each one of those letters represents one of these 4 dimensions of depth. Okay? The first one being, right, first of all here, I skipped a little bit here, but basically what we're doing here, we're taking I showed you an example of taking some random image, and I reshape it to do its 2028 image right here. And basically, I used the reshape function. We did this again, I think 2 weeks ago. And that reshape function basically sets it into the right pixel size, the right dimensions of that image. So here, that single array is now 3x3. All right. So I do that here. I just take some random image from my data set. I reshape it. And I want to convert that into an image to view to see what's there. From here, before I do that, I took the long way around just to show you guys. I showed you guys this image stuff. And basically what happens here is, here, when I load this up, it's an RGBA image, which means it has 4 channels. Each one of those channels is a different dimension, in that 2x2 array, right? If that's the way you want to think about it. Think about this 2x2 array that has 464 rows, 934 columns. That basically has 4 sets of them behind each other, all right? 4 sets of them behind each other, right? Why? It's an RGB image. The first set of data. So let me go back to my trusted Excel sheet again. All right, here, let's say we have a 3x3 image, right? 3x3 image. Now, if it's an RGBA image, unlike our MNIST data, which is just black and white data is just 2x2. That's easy, right? But the RGBA image, and for some of you guys, RGB image, some of you guys loaded up a GIF or JPEG, that will only have 3 dimensions as opposed to 4. Don't freak out. It's because GIF and JPEGs only have 3 dimensions. They don't have that 4th dimension, which is basically transparency. All right? So here, this 3x3 image, right, it has the first dimension, 3 by 3 image. It has the second dimension, 0, 1, 2, and 3, all 4 dimensions. The first dimension over here is the color red. That's a small font. Make it bigger. This controls how much red is in your pixels. Again, this is an image that has 3 by 3 pixels. All right, 3 across, 3 across. The second dimension controls how much, again, RGBA. R for red, G for green. The third one, B, RGB, blue. And the last one is what we call alpha for A. What is alpha? Alpha basically means transparency. All right. The highest alpha gives you a solid color. The 0 alpha gives you complete transparency. You can't see the color at all. This is what these dimensions are happening. So the first dimension, those numbers represent how much red is in the pixel. The second one dimension is how much green, how much blue, and then how much alpha. For any guys that know TVs or your phone screens or whatever, all these colors are a combination of red, green, and blue. Red, green, and blue. And I guys gave you the example of how, for example, the orange is basically the combination of 255 red, 128 green, and 0 blue. Now, what is that number 255? Okay? The amount of red, green, blue, and alpha that is given to any pixel, the amount, it's from 0, which means no red, all the way to 255, which means full-on red, and every number in between. That is how all these different colors are done, 0 to 255. Now, that 0 and 255, we can now go back and talk about here, what is this uint8? Okay, so when you create your images and you convert them to NumPy arrays, or vice versa, you create images from NumPy arrays and you load them up and you're creating images from NumPy arrays, the type is very specific. It is a uint8. The int obviously means integer. The 8 is a very small integer. In fact, it's an integer that only goes from 0 to, you guessed it, 255. It's very specific. It only allows numbers from 0 to 55. That u over there means unassigned. That means it can only be positive. You can't have any negative numbers. It can only be positive. Only positive numbers from 0 to 255, which maps perfectly to the whole RGBA schematics of colors. That's why that type was uint8, and that's why here, when we made our own 2 boxes, when we made our own 2 images, these 2 boxes side by side, did we do that here? Or we started that? We made the types explicitly uint8, right? Because here, np.zeros, if you remember, this is just simply I'm creating a NumPy array full of zeros. And here, what's the dimensions of this NumPy array? Y. It is simply going to be 100 rows, 200 columns, and 4 dimensions. So this will be a 3 by 3. This will be a cube, or a third-dimensional NumPy array. All right. Now I'm creating. If you remember, I'm creating 2 boxes side by side. These boxes will have dimension 100 by 100, 100 by 100. This is why I have 100 rows and 200 columns. So the 2 boxes are side by side. And I have the 4 dimensions because I'm making this into an RGBA image. And because of the fact that it's going to be an image, it has to be explicitly given the data type uint8. Done. All right, go ahead and run this. This is all 0. Right, at this point, I want to make the left box, just the left box, all red. Okay, so if I make it all red, this is where I was showing you this example. All right, here, I'm making the left box all red. Now look at how I'm slicing this, guys. I'm saying this is remember, this is a 3-dimensional NumPy array. Here, I'm saying all the rows, right, to the left of the comma, and I'm saying to the right of the comma, all the columns from the 0 Remember, there's a colon. Colon means start from the beginning if it's on the left side. From 0 to 100, to the 100th column, but not including the 100th column. So basically, from 0 to 99. So basically, all the 100 rows, but only for the columns, only for the first 100 columns, which, ladies and gentlemen, makes a square. And now I select that region, but I'm only giving the coordinates for the rows and columns. I'm not giving coordinates for the dimensions. But look what I do. I select those rows and columns, and then I say, set those coordinates equal to this list, 255, 0, 0, 255. What's happening there? What's happening there is, because of the fact I didn't explicitly choose the third dimension, the third dimension, any of the depths, right? The 4 depths, right? Or what we call the z-axis, if you will. The z-axis always, x represents the horizontal, the rows, y represents the columns, and z in geometry represents the third dimension, or the depth. But because I didn't select that, I just selected the x and the y's, right? And then I said, oh, here's 4 numbers, go set it equal to that. Well, what does that mean? That means, because of the fact I have 4 dimensions, the way these values will be placed in those boxes will be such as this. 255 in the first dimension, 0 in the second, 0 in the third, and 255 in the fourth. And that will happen to each cell in this region. A great example of this is here. If we just take the first cell all the way in top left, all the way in the corner. All right? The first row, first column, the first dimension is 255. Again, sorry about this. Let me make the fonts bigger for all these bad boys. 36, done. All right, good. You can see that now. 255. Because it's the first dimension. All right. Here, the first row, first column, second dimension, make that 1. Make that 0. Okay. First dimension, first row, first column, but second dimension, make that 0. Done. Again, first row, first column, third dimension, make that 0. First row, first column, but third dimension, make that 0. All right? First row, first column, fourth dimension, make it 255. First row, first column, fourth dimension, 255. This is why stacks. So here I have them side by side, but in reality they're stacked in depth behind one another, that first corner cell. But in actuality, this is just for one cell. I did these values right here, like over here, these values. I went ahead and I did it for the whole region of that square region, being all the rows and the first 100 columns. That's what ends up happening, right? And without looking at anything else, because of the fact I told you the RGBA rule, you know what the color of that square is going to be. The dimension that represents red, the first dimension, it's full on 255. It's full on red. The dimension that represents green is 0. There is no green. The dimension that represents blue, there is no blue. It's 0. And the dimension that represents opacity is full on solid color, 255. So what's that square going to be? It's going to be red. Now we go to the second column. The second square. I'm again selecting all the rows, but this time I'm selecting all the rows and the second set of 100 columns. And again, I'm setting all the dimensions, the 4 dimensions of each one of those squares to be now 0, 0, 255, 255. So all the reds will be 0 now. All the greens will be 0. But the blue now will be full on 255. And the transparency will be full on solid 255. So what is that square going to be? that square is going to be blue. That's how colors are done in these images. They're done in the third dimension. All right, so let's go ahead and run this. And now I'm going to use my image class from here to go ahead and convert this into an image. And I'm going to save this image. I'll call it on my MG3 because I think I've done this quite a couple times. And I'll save it, and it's going to save to whatever folder's up here in your top right that you selected. Right, and I go to that folder, scroll down, and I have something called My Image 3. I click on it. Ladies and gentlemen, you just made an image straight from NumPy code. Yes, it's a simple image, but whatever. You have a red square and a blue square. By all means, please play with this. Don't use the color as I do. Use a totally different composition of colors. Online, they have the whole RGB map. Now from here, let's have a little fun. Where's my slide? From here, let's have a little fun. Let's make the image a little bit cooler, all right? Let's mess around with the transparency so the image actually looks a little bit cooler. So what I'm going to do is I'm going to change for each column in the red and the blue, I'm going to change the transparency ever so slightly. So for here, what I'm going to do is, for the red, again, all the rows up the first 400 columns, I'm changing. Notice now I have a third dimension in here. I have a second comma, a third dimension, because I'm just changing the fourth image, which is the alpha, which is the transparency. And there what I'm saying is, you know what? Instead of all being the same transparency, let's make it all different transparencies. Column by column by column by column. All right? So what's going to happen is the first column, all the rows, is going to have the transparency of 156. Notice I'm using a range here, guys. This is going to give me values from 156 to 256, not including 256. So it'll go up to 255. All right? 100 values. It has to be perfectly 100 values to map the 100 values I'm selecting here. So what's going to happen is 156 here, right? I'm selecting a square here, but here I just have an array of values. So how does this play out? It plays out like this. Each one of these values, 156, will be repeated downward in each column. So the first column, column 0, for all the rows for column 0, all the transparencies will become 156. For the second column, all the rows in the second column, transparency will become 157. In the third column, for all the rows, transparency will become 158, and so on, and so on, and so on. Right? So let's go ahead and do that. I shall do exmp, all the rows, the first 100 columns, just the last dimension, and I'm going to now set it to, I'm going to be a little more aggressive. Right, I'm going to be a little more aggressive. Before I did 150 to 256, so I'm going to do it to 100 to 200. 100 to 200. All right. All right, and now I'm going to do the same thing for this guy. This is obviously going to be my blue one. And for the blue, I'm going to make it, I guess I'll make it not as aggressive. I'll do 150 to 250. All right. Okay. And now I'm going to go ahead and create a new image all over again. This time I'll give it a different variable. I'll call it my image 4. And I'll save it as my image 4. I come down here to my folder, click on it, make this bigger. And you see how much more depth this image has? It's because I'm using transparency. Obviously the red one is lighter than the blue one, but there's more depth because I was more aggressive in the transparency part of the red versus the blue. So here you can be artists, guys, using your different using your different NumPy arrays and just playing with the pixels and everything like that, right? And obviously, this is how a lot of code works. So from here, all right, from here, I go back to my Tesla image, right? My Tesla image here. Now let's mess around with the Tesla image. Let's say, okay, I want to make all these, for all the rows, let's get rid of the greens. No greens. Now, to get rid of the greens basically means is take the, remember, RGBA, the second dimension, that's why there's a 1 here, make them all 0. Make them all 0. Right, so I will grab my Tesla NP here. In fact, let me make this, apologize, let me make this all bigger so it's easier to see. Probably should have done that before, I apologize. But now I have Tesla NP, and now I'm going to say, for all the rows, all the columns, just this, for all the rows, all the columns, make the second dimension, which is 1, apologize, make it 0. That means there's going to be no green. I go ahead, I run that, and what I'm going to do is I'm going to create a new Tesla image from that NumPy array. Let me take this and say image from array Tesla NP, and I'll call this image Tesla 2, and I'll save it as Tesla 2. Okay, fine, I saved this, whatever, it's fine. I had a different name. I think I already have Tesla 2, so let me save this as Tesla 3. A little confusing. Go here, go to Tesla 3, and what do you see? You see that it's all pink. Why? What happened? All the white kind of disappeared. What happened? It's because we got rid of the greens. If you guys remember from science class, the way light works is that white is 255 red, 255 green, and 255 blue. You need all the colors for white. You need all the colors white. That's why black is just 0, 0, 0. It's a void of all colors. Once we pulled away the green, all that's left is what? Red and blue. Everything becomes violet and purplish. So that's basically what happened in our picture here. All right, so that's a little introduction to images. Now let's get back to business at hand. All right, so I took that random image from, I believe, the 36,000th image, random image. I reshaped it, and now I want to convert it into a actual, it's in a proper NumPy array, 28 by 28 pixels, and I want to convert that into an image. All right, let's go ahead and use image to see what it looks like. All right, and here now I'm going to actually start using PyPlot to do this, because PyPlot allows me to show the image directly in my Python, in my Spider output console. Right, so here I'm going to do, first I want to do my image from array. Save this as an image, and we'll call this some digit image. I will name it even anything you want, SDI for short. And this time, instead of saving it, you could save it if you want, but because I'm using matplotlib, I can now show this image directly in my console. Right, so I have that SDI, and from here, I'm doing plt im show. I want to show this. That's a command. Image show SDI, right? And the axis off is basically, it's there because when you do plt show, and that actually shows the image. Highlight both of them at one time. You see you get the image, and the image is what? It's a black and white 9. It's in black and white 9. But you notice this axis you have here, it literally has those pixels, the dimensions. That's why we have this extra part right here, plt.axis_off, right before the show, right? Just to get rid of those numbers on the side. I mean, it's not a big deal. You can leave them there if you want. It's totally up to you. Oh, assist. Typo. Can't type for some reason. Boom. Right? Nice clean image of a 9. That image is a 9, and we can confirm that because we have the, guys, we have the target right there, right? And so the target array has the right answer. So if I were to do target 36,000, what does it say? It says a 9. Notice the quotes there? I don't know if you guys can see it, it's kind of small. But it's if you're doing it following along, if you see the quotes there, the target number values are not stored as numbers, they're stored as actual strings. That's what the whole thing's an object. I don't know why they do that. It takes up more space, but whatever. We just go with it. All right, so here I have my 3600. Now from here, all right, from here, guys, I want to show you now something else called the PLT IM show. Before we just image show, we just did it. We didn't give any sort of values. I just put the STI image in there. But if I were to use pure matplotlib, right? So let's do some digit image. I want to show you guys this. All right, have the actual some digit image right there. And then, comma, CMAP. What is CMAP? CMAP stands for color map. Okay? What is color map? There are tons of color maps in the world of Matplotlib. What do? What are their purposes? Their purposes are to put a color to the variation in numbers. Okay? What does that mean? What's the purpose behind it? Basically, it gives you different, you guys have seen this in Spider. When I have opened up tables and you see that the numbers have different colors or shades in the background. What happens is, the world of Matplotlib, numbers are hard to see, especially large numbers, large amounts of numbers, but colors are easier to see. So the number 5, let's say you have 3 values, 5, 100, and 5,000. 5 would be shown with a background of a certain image, color. 100 would be shown with a different kind of color, a more stronger color, whereas the 100,000 part would be shown with an extremely strong color. Those different shades of the color gives the variation of the numbers. That's the whole point of color maps, right? It's a way to show the range of your numbers in a data set using visual analytics. If my ABI students remember, we talked about visual analytics. The color maps aids in that process by giving shades according to how the difference between different numbers. So in this case, the color map I want to use is the binary one, black and white. Matplotlib, matplotlib.cm color maps.binary, right? And the weave part, don't worry about the weave part, the interpolation part nearest, that basically means how do you want the colors to blend into each other. And it's very easy. We just want the nearest color, whatever the nearest color is, to take it. Interpolation equals nearest. Right, I go ahead and I execute this. And what do we see? You see a nice, let me scroll over here a little bit. Boom. You see a black and white 9. What's up with that? The colors are reversed. What's going on? The difference is, before, these numbers were, the original numbers are the right ones. Those numbers correspond to what an actual image is. These colors and numbers are just are being mapped according to how different the numbers are. All right, so 0 here would come as white, whereas 0 in the world of images comes as black. Okay, and we could play with this, right? We could play with this. If we chose, instead of a totally different CM binary, instead of CM binary, we chose CM Spring. All right, CM Spring. And by the way, I didn't choose axis off or anything like that. That's why the axes are there. But we can add that as well. Scroll way down again. All right. And instead of CM binary, I choose CM Spring, which is one of, again, many color maps out there. Have axis off. Let me just copy this. Go ahead and run this. Ta-da! It's now pink and yellow. Again, why is it pink and yellow? It's because the way this particular color map, the spring color map, works. Smaller numbers are given pink. Larger numbers are given yellow or probably whitish, some yellowish or whitish color. You see how it makes it discerns the number magnitude by colors visually. That's the whole point. Whereas binary, it was the opposite way. Binary, the smaller number was 0, the larger numbers were black, and that's how it discerns the difference in those numbers. So that's basically the gist of what's going on here, guys. All right, cool. Now, we know that's a 9, and we can get back on track now here. All right. We know it's a 9. Now we are ready to start talking about training our data. All right. Now, we want to train our classification model to basically be able to look at these images like this 9 and say, hey, it's a 9. All right. The data we have, right, if you notice I did target, this is the actual right value. And the data 3, the one I did up here in line, line 20 and 21, that was the actual image. We want to basically feed these images and the right answer into a classifier so it could train itself to basically say, oh, okay, anything that looks like this is a 9. Anything that looks like the 1s in our data set looks like a 1. Anything that looks like 2s are a 2, and so on, so on, so on. All right? Now, one, I just have to say, you're beholden to the quality and the magnitude of your data. That's why a lot of data scientists and a lot of, obviously, in the hedge fund world, right, the world I'm in, these quantitative investment funds, it's all about data. It's all about data. The more data you have, the better your classification models will be. And this is why they have these massive data lakes. They're using AWS, Azure, Cloud, Google Cloud, to store all this data and process it and to make their machine learning algorithms that much better, right, over and over again. Right, so it obviously all starts with data. But nevertheless, right, we have this data that we want to train a classifier. Now, when you do this, it's important to allocate a majority of your data to train the model, but we don't allocate it all. Now, some of you guys already have machine learning, you already know this. For you newbies, what we do is we like to save some of our data to test our classification model, all right, to make sure that it's effective and it's accurate. All right, now, the MNIST data, remember, it has 70,000. If I scroll over a little bit here. Data has 70,000 rows. Again, that means 70,000 images, right? It already does a lot of the work for us in the sense that the first 60,000 rows are meant for training. The last 10,000 rows are meant for testing, all right? It does that work for us. We're going to go ahead and we'll just go ahead and grab it. Here, what we want to do is we want to take our data and we want to split it out into our training and into our training and our testing data. So when we do that, we don't only split out the actual data, we have to split out the target as well. I mean, which is, by target, we mean whatever the right answer is, the right answer part. All right, so here, notice what I'm doing. I'm saying, okay, the first 60,000 rows from 0 to 59,999, that's this new variable, data train. The last 10,000 will be our test data test. All right. If we go to our target data, the first 60,000 rows just corresponds with data as well, is our target training. That's our target data for training. And our last 10,000 rows is for testing, our target for testing, right? And again, here's a nice visual for what's really going on here, right? We're breaking out. This right here is going to be our data train. This right here is going to be our data test, okay? Let's go ahead and do that. I think we could just copy this, data train, data. Remember, it's going to be the first 60,000 rows. I'm doing a little bit different order. All right, and then I'll do my test. Data test. It's going to be the last 10,000 rows. Okay, so lines 55 and lines 56 is what we're going to use to train our data. Lines 58 and 59 is what we're going to use to test our data. Alrighty, we've broken up our data. Now, from here, what I'd like to show is, again, how the numbers, I just wanted to show you this function called np.unique. And what this allows you to do is np.unique on, for example, let's do it on the sum digit variable. It was a 36,000th image. And what we could do is we could basically count up and see how much empty space there is, or how the number makeup is of the arrays, right? If you add this parameter called return count equals true. Let me just copy this and I'll just edit it right there. Right? And then here, you see this results right here on the sides, right? You see two arrays. You see this first array over here. It's kind of small on my monitor, but on your monitor, you'll see the output will have two arrays over here. Well, I mean one array and the second array over here. What's basically going on here? Well, the first array, when you run np.unique, is all these unique values, right? That's number one. The second array is going to be, so right here, if this is the 0 value, right? My first array. In my second array over here, it's showing how many times that 0 value is in that some digit array. So 604, I have 634 zeros. I have a 2, that's there once. I have a 3, that's there once, etc., etc., etc. After, if you go to the bound of the second array, the next number that there's a lot of values for is 66, and that's the second to last value. If you go over up here, is 253. So 253, the number 253 shows up 66 times. Why do I bring this up? Well, one, to show you this functionality, what it does, and two, to show you that, hey, this image, this 9 that we created is basically, I mean, there's a lot of numbers involved, but it's basically just zeros and 253s, right? 0 and 253s, and it's a black and white image. Black and white images, the color images, the RGB images, and the RGB images, they're three-dimensional arrays. The black and white images are a special two-dimensional array. They take up less memory, and the reason is because their colors are just defined between 0 and black. Basically, just 0 and black. 0 to 55, white to black. white to black, and everything in between is gray. So, I mean, this gives you a little insight into why we're using the MNIST data set. It's black and white. But more importantly, it goes to show you how adding any kind of color, any kind of transparency, how much more memory it takes in these kind of images. This comes into play because a lot of times in machine learning, what they do is they'll take the data and they'll simplify the data or transform it into a simpler format before they do any kind of machine learning or classification or any kind of training on it, because it just saves so much more memory if they can get away with it, right? If they can get away with it. So that's a nifty little function, just to give you a little insight into what's happening with the numbers. All right. So we broke out our data into our training set in our testing set. Now look, the rule is basically, I don't know if I talk about the rule, but usually the rule is, I guess I didn't write it in my slides, but usually what they like to do is about roughly 2/3 of the data they like to conserve for training, and about roughly 1/3 for testing. Now listen, this is I mean, this could also be like a 70%, 80% for training, and another 25 or 20% for testing. It really depends on your project, but majority of the data is always set aside for training, and the minority of the data is set aside for testing. Now, we also need to shuffle our training data. Why will we need to shuffle our training data? Well, because a lot of algorithms and classifiers, they will perform very poorly if they get many similar instances in a row. What that means is if our data is basically all the zeros first, then the ones, then the twos, then the threes, then the fours, and that's how our model is being training, well, it's going to be trained very poorly, right? A lot of classifier models work this way, right? So we're going to bring a new package within NumPy called random permutation to allow us to shuffle the data. How does this work? Well, real simple. Let's just call np.random.permutations on the number 4. All right? Oh, sorry, it's permutation, not permutations. All right, what you see in my output, again, my output is going to be small here for you guys, but I have the output 0, 1, 2, 3. Okay? Which wasn't random at all. Let me just rerun that again. I mean, that was random, but whatever. Okay, and the next execution, I got 1, 2, 3, 0. All right, and I'm sure if you guys run this a couple of times, you guys will see the same thing. What ends up happening here is all the numbers up to 4, 0, 1, 2, 3, they keep coming in different orders every time you run this. It's random. It's completely random. What's happening here? Okay, well, how am I going to use this function or the results from this function to basically shuffle my data? All right, well, what's happening here is I'm going to go ahead and put the number 60,000 in there instead of the number 4. And now it's going to give me a total randomized order of numbers from 0 to 59,999. All right, I'll call that shuffle. All right, so now I have this variable called shuffle. That's basically all it is the number 0 all the way to 59,999 in random order. All right, those numbers all in random order. How am I going to use this array of numbers or random numbers to now shuffle my data? Well, I'm simply going to pass that shuffle into my data train and my target train and get the new order. How is this working? What's going on here? Well, basically, if you want to think about it, all right, if I go to my trusty Excel sheet, It's bigger. All right, so let's say we have this array here, right? Say we have this array here. Assume this is our training data right here, right? Our training data has 36, has 4 rows. Our training data is very small, has only 4 rows, right? And with some random numbers in here. So this is one image, this is another image. This is my third image, is my fourth image, okay? Now, let's assume the name of this is X. All right? Now, so this is the order of my X. If I were to hypothetically type in, have a variable or a vector that had the variable, let's say A, so I make that bigger. Let's say A was the random order of whatever, 2, 1, 3, and 0. Right? For argument's sake. Let's say that's what A is. All right? Now, if I were to type in up here X of A in my 2 by 2 array, what's going to happen? First off, notice A is a vector of values. Done. I'm basically slicing here, guys. I'm slicing, but I'm just slicing the rows. There's no commas. It's just X of A. There's no X of A comma anything. So I'm not slicing the rows columns, just the rows. Okay? It's the equivalent if I did X of 0 gives me what? It gives me this row. X of 1 gives me this. X of 2 gives me this. X of 3 gives me this. Right? But if I do X of A, X equals X of A, what ends up happening? This is what ends up happening. Okay? The first value in the new X will be the first row we sliced from A. 2. This one. Let me just make these different colors to differentiate different images. This is the yellow image. This is a light baby blue image. This is the green image, and this is the purple image. Or okay, orange, whatever. So the first one now becomes 2. Okay. Take this. And now it's the first one. Well, the second one in the order now becomes 1. Take this. That's there. The third one is the last one. And now the last one was originally the first one. And as you can see, now what happened to X, we shuffled those colors around, right? We shuffled those colors around using this methodology. That is exactly what's happening here with the shuffle. That's exactly what's happening in the shuffle. In the shuffle, it's random numbers from 0 to 50,000 to 500, 999, all shuffled up, all randomly just picked. It's put within the data train in the order and set equal to data train here. And now data train in order, the rows are all shuffled up. But it's important that whatever way we shuffle up data train, the actual answers are also shuffled in the same order. Okay, if we go back here, remember each image has its actual value. So whatever way this is shuffled, the image side, the actual value also must be shuffled. All right, that is why we have it saved in a variable. And that's how it gets shuffled, right? And we do it in one shot because every time you run the shuffle command, line 1, it's going to give you a different order. That's why we have the variable first. We ran this part first, and we're going to use it to shuffle both sets of data. Okay? Let's go ahead and do that. Done. Done. And now we have everything ordered. Okay. And so now looks like we're ready to go, right? But before we go ahead and train our image to run on all those different, train our classifier to run on all those images, I'm going to go ahead and first do it on a binary set of data. What do I mean? I'm going to solve a simpler problem first. I'm going to train my model, my classifier, to just identify one digit. For example, let's choose the number 5. This is an example of a binary classifier capable of distinguishing just between two classes, 5s and not 5s. All right, two classes, 5s and not 5s. We're going to do this, all we need to do is essentially transform our target data to, instead of being numbers of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, to instead just being true and falses. Trues for the 5, falses for all the 9 5s. All right? So the values are going to be Booleans instead, not numbers. So I need a new target data. I need a new target array for my target train. All right? What am I going to do? I'm basically, how do I convert my data from numbers to trues and falses? Very simple. We're just going to do a Boolean condition right here. This is in my slide. I'm sorry, it just becomes one giant equals with no space in between. This is basically equals right here. This is just basically equals. There's just no space for some reason, and we're just doing a check. We're saying, look, target underscore train equals 5. Notice it has to be in quotes because the target numbers aren't in numbers; they're text for some reason. Okay. This is a conditional check. So what ends up happening is any value, again, this is vector conditionals we're doing here. This is a data container. So every element in this data container will be checked to see if it's 5 or not, equal to this value. If it is, it gives back the value true. If it's not, it gives the value false. And that's why this over here will become an array of true and falses. And same thing with our target test. This will target test 5 will become an array of true and falses. All right. I don't think we need to do it for our target test yet. Let's just do it on our training target data for now. So I'll just call this target train 5 equals target train equals 5. All right. I go ahead, I run this, and now if I run the np.unique command on target train 5, you see it's now an array of just true and false values. Okay, real easy. Our images are still images. It's just that their answers will either be false or true, depending on if the image is supposed to be a 5, it'll be true. If it's a non-5 number, it's going to be false. All right, real simple. So we just converted our data into a binary, basically a binary problem, so we can make a binary classifier. All right, now let's choose a binary classifier model. All right, we have to choose a classifier and train it with it. What are classifiers? Classifiers are predefined models, machine learning models, that do the classification for us, right? That are trained to do classification, that are written to do classification. There's a whole bunch of these preloaded up into Scikit-Learn and other machine learning packages. One particular one is called stochastic gradient descent model. All right. Later on, I just throw this on to you guys for now. Later on, we'll talk about what's going on in the background with stochastic gradient descent and some of the other classifiers we talk about, right? But for now, the advantage of this particular classifier, its capability, one of the advantages of using the stochastic gradient descent is that it's very capable of handling large data sets very efficiently because of the way it's designed and the way it works. All right. So we'll use this for now. Now, if I want to pull this data set in, I'm going to call it from the linear models of Scikit-Learn, right? And import the classifier SGD classifier, right? That's the function that does the stochastic gradient descent classification. All right. In addition to that, after I get that classifier, I'm going to run it. I'm going to declare a variable that will represent it, so I can use it over again to train the data. Now, notice in the parentheses, so again, this part right here, this is the actual name of the classifier. This part is just a variable. You can name it anything you would like. Name it Corona, whatever you want. I just call it SGD for short. In the parentheses, notice I put this random underscore state equals 100. Well, what's happening here? My ABI students, this should be familiar to you. There is, when using this algorithm, there is a element of randomness using this classifier. Like there's simulations going in the background, there's random numbers being generated in the background. If you want to have consistent results when you run this over and over and over again, this random underscore state equals 100, what it does is it allows you to choose the same set of random numbers over and over and over again when you're doing analysis. You see, whenever you're doing simulations involves a lot of, or simulations or any kind of algorithm that uses simulations or any kind of random numbers to do to test that data over that methodology over and over again. The problem is that your numbers keep changing. Those random numbers keep changing. This is why these random number generators, they allow you to say, hey, just choose the same set of random numbers from before. And so that's what I'm doing here. Random underscore state equals 100 to keep my random numbers consistent. All right. And then this SGD.fit, what is it doing? Very simply, it's fitting the model. It's doing the training. It's that easy. The first parameter is your data that you want to classify. Is your training data that you want the model to learn to classify. In this case, our images. And our second parameter, you're telling the classifier model what the results should be from the training data, right? So it looks at the training data, each item of the training data, and then it looks at what the answer is of each item of the training data, and it slowly learns, not slowly, but it learns, okay, so if I get an image that's a 5, I want it to be, the answer to be true. If I get an image that's 0, 1, 2, 3, 4, 6, 7, 8, 9, I want the answer to be false. This is what, it's all happening here. Very simple, right? All right, very simple. So let's go ahead and do this part right here. I'm going to go and copy this, and I'll fix it up. Oops. Kind of ugly. So I'm importing my classifier right here, guys. I got declared my variable, and I'll train my data. All right, I should be good to go from here. Oh, that's underscore, not dot. There we go. All right, so here, let me do my, from Scikit-Learn, model import GD classifier. I believe, oh, Scikit-Learn.model, sorry. Sk.linear model, here we go. Now we should get rid of that error. And now I can import. Excellent. Here, I'm just going to underscore there as well. There we go. So now I declare my variable SGD as a SGD classifier with a preset random state I want, 100. You can choose any number you want. There's a whole mess of numbers. And I'm going to fit the data, basically train the data. And then you see, when you run that, the fit part, notice you get all this other stuff coming out. Mostly it's warnings. They're talking about the nuances of things changing in the classifying model. All right? And all this other, so many more details we can apply to it. All right? It's fine. As long as you don't see an error, it's fine. You will always see the verbose sort of warnings and new features and what's changing coming out. All right, so there we go. Our model's trained. Now, real quick, let's predict our sum digit. Right, remember, what was our sum digit? I believe our sum digit, if you remember from before, it was 9. Right, I believe it was 9. So let's do SGD dot predict. And remember, sum digit, guys, again. All right, what's sum digit? Sum digit is just the array of the image of our 3600th row, which we found out to be, I mean, if you forgot, we could run it again. Let's see, if you go up here, NP, sum digit up here, right here, I like this one. All right, it's number 9. It's basically number 9. So if I predict this, what's the answer going to be? You guys can't see it here in my output, but I'm sure you can see it on your machine. I got the answer false. Hopefully you guys got the answer false too. And this, ladies and gentlemen, we just did a prediction. We trained our model and we predicted it on a one particular image, in this one 9, and we got the right answer. Yay, it's false. All right, happy ending, right? Notice, by the way, even though it's just one image, I still have to pass it in as a list. Okay, a list of even though it's a list of just one array, I pass it in as just one list. Now, we want to now evaluate how effective the classifier is. Right? Now comes the more mathematical, annoying part. This part's easy. But just like an ABI, yeah, that's fantastic. But is the model actually giving you any kind of results of substance, or is it just rubbish? This is where performance measures come into play in machine learning. All right, so at this point, I'll end this video. I'm going to break up the video into 2 parts, only because I'm having a problem with uploading and the quality of some of these videos. So I'm going to end this video at this part. It should be around roughly an hour and 20 minutes. And now I'm going to have part 2, and we're going to continue on to the part 2 of this lab. All right.